Alright, so today to wrap up the unit, I want to look at two things. One is simply an application of a couple of different things that we've done. And we're going to start there, and then we're going to look at the concept of slant asymptotes. Alright, so what I want to do is, to start here, is kind of use this as a warm-up. You actually know how to do all of this. The main thing is the question on part B, where we are relating the idea of our horizontal asymptote to the situation, okay? Let's read through the problem. Now I'm going to give you guys a couple of minutes to think through it on your own and do these two parts of it, okay? It says, for a person with sensitive skin, the amount of time, T, in hours, the person can be exposed to the sun with minimal burning can be modeled by the equation T equals 0.37 S plus 23.8 all over S. And S goes from 0 to 120, and it's the sensor scale reading. Okay, the sensor scale is based on the level of intensity of UVB rays. Okay, so let's just think about the concept. We're in Florida, so we should be kind of familiar with this idea. All right, if S is higher, what does that tell us about the sun that day?
Pretty strong.
It's getting, it's stronger, it's more intense. So you're more likely to burn
Quicker.
faster, quicker. So time should be decreasing, right?
Yes.
If you think about this, guys, time should be decreasing as S gets greater, or gets larger, closer to 120, okay? So keep that in mind as you work through A and B. Let me give you a couple minutes here to work on those, and then we'll talk about your answer. Okay, let's take a look at our answers here, see what you guys came up with, and then discuss part B particularly, all right? So part A, we had different values of S, that's our independent variable. T, the amount of time that you can spend outside without getting a sunburn is dependent on the intensity of the sun. So T in this case is our dependent variable. So when S is 10, how long can you stay out? 2.75 hours, okay? How about when S is 25?
1.322.
Okay. And once we reach 100,
0.608.
608?
Yeah.
Okay. So about 6/10 of an hour. So that's about 36 minutes that you could spend out when it's that intense without getting burned. Okay? That's what that's telling us. All right? You'll start to burn after about 36 minutes if you've got sensitive skin. All right? You guys being around here, you know how that is. There's some days that you can just feel it. It's more intense. If you watch the weather on the news, they'll tell you what the UV index is. That's kind of similar to this sensor scale, but it's just measuring the intensity of the sun. But let's talk about part B, okay? The model, if the model were valid for all S's greater than 0, what would be the horizontal asymptote of this function? So what would our horizontal asymptote be first?
1.37.
Okay? You guys agree with that?
Yeah.
Okay.
Y.
Okay. Y equals 0.37. All right. We have a rational function, right?
Yes.
And the degree on the top is 1. The degree on the bottom is 1. So we find the asymptote by the leading coefficients. Good. The ratio of the leading coefficients. So 0.37 over 1 is just 0.37. So Y equals 0.37. Now this is what I really wanted you guys to understand here. What does this represent? Yes.
Where you, it's the point where you won't be able to go outside. Like where the sun will be so powerful that if you
You'll
step
burn like a
outside for
second.
a second, you'll just melt.
Okay, what do you guys think about that?
Isn't all the, it's like approaching this line, like all of the, like the hours will get closer and closer to 0.37, but like we'll never touch it.
Okay, good. So actually for our y, we really should be saying, instead of y, we should be saying
Time.
T.
time equals 0.37, right? And that's hours. So, okay, she's saying that our time is approaching 0.37. Is it approaching it from the top or the bottom? From the top. So our times are getting smaller the greater the intensity of the sun on that day, right?
So you'll burn, like, no matter how strong the sun is, you'll burn in 0.37 seconds when it's at its max.
Yeah.
We are on the right track. Okay, we're on the right track. No matter, let's take part of that. No matter how intense the sun is,
You'll burn.
that's the key there with that asymptote. As S approaches infinity, no matter how big S gets,
S will never, T, like,
It'll never-
it'll never
There'll
get
never be
there.
a time when you walk outside
And you don't
and you're gonna
burn.
burn up in 1 minute.
No.
No matter how
They say-
strong the sun is.
It'll never be
okay,
instant.
let's
You're
keep
never
going
gonna-
with that.
You're never gonna burn in less than 0.37 hours.
After 0.37 hours, you can burn no more.
You can't.
No,
negative
you'll never burn
No.
in less time than 0.37 hours.
Okay, there you go. And no matter how intense the sun is,
burn.
you'll never burn in less than 0.37 hours, which is approximately, like, I think we said 22 minutes or so. So here's the deal. No matter how hot the day is, no matter how intense the sun is, that asymptote is saying you can safely stay outside for 22 minutes and not burn. Okay? That's what this asymptote is telling us. It's the minimum amount of time that you can spend out without burning, no matter how intense the sun is. Okay? Or in other words, it's the maximum amount of time that you could spend outside and guarantee that you'll never burn. Okay?
So as soon as you're outside for 22.1 minutes, you're burning.
You'll start to burn, theoretically, yeah. You'll start to burn. Okay? So if you have no sunblock for some reason, you have kind of a window of time here, based on this model at least, for how long you can safely stay out. You know, so maybe you can go out for 22 minutes, come back inside for a while, cool off, then you can go out for another 22 minutes maybe later, you'll be okay, come back inside, cool off, all right? But this gives you a window of time where you won't burn no matter how intense the sun is, okay? So kind of an interesting application there. But this is a thing that we can use asymptotes for, all right? And if you think about it, there are a lot of different things, and we'll talk more about this as we get into our next unit here with exponential and logarithmic growth and decay. There are things where we use these asymptotes to kind of find a realistic minimum, okay? One example is like if we had the Olympics last summer, and every time, every Olympics we break certain world records, for speed. Well, physically, there is a limit to how fast humans can move, I mean, I used to do kind of an activity with my Algebra 1 students when we were studying lines and slopes of lines and that sort of thing. I'd give them 2 world records, and I'd have them figure out when the world record would hit 0. All right? So he said, that's going to be the year we discover teleportation, because we covered a 100-yard dash in 0 seconds. And obviously it's ridiculous, but the idea though is you have an exponential. Every time we beat the record, it's by a smaller and smaller and smaller margin, okay? If you look at old videos of the Olympics, you know, their clocks were in tenths of a second, you know, because back then that was precise enough to be able to tell who was winning. Now we have them down to like the thousandth of a second for you know, running a race, because our world record might only be beaten by a few thousandths of a second. And who knows, maybe they're going to need to get one down to the 10,000ths of a second someday soon. All right? Because the amount that you're beating the records by is smaller and smaller because it's leveling off. We're approaching, I don't know how quickly we're approaching it, but we're approaching the kind of limit of human existence, you know, where it's not going to be physically possible to go any faster. Who knows what that is.
I remember in one of my track meets, I was in 8th grade, and we were doing a 4x8, and we were trying, this was like a qualifying meet for states, and our 4x8 was 1/10 of a second from getting to states. Like, they picked the top 4x8 teams, and we were 5th by a 10th of a second.
Yeah.
And we were out, we couldn't go.
So yeah, so you know, we have to, you're measuring by smaller and smaller increments, you know, because as time goes on, we're going to beat certain records, but it's only going to be by a tiny amount. So, all right, so one other action I want to look at here is kind of an extension of what we looked at with our rational functions, and that is cases where we have a slant asymptote. All right, here's a function y equals negative 3x squared plus 2 over x minus 1. Okay, now let's talk about these first three parts here. Okay, first of all, as you look at this rational function, what's our domain?
X cannot equal 1.
X cannot equal 1. All right, good. X cannot equal 1. Is that going to give us a vertical asymptote, or will that give us a hole?
A hole.
Why?
Because there's nothing, you can't, the vertical asymptote you find after you find the discontinuities in the holes, I think.
Is that right?
I can't remember. I'm mixed up with one of them.
What, Ahmad?
It's the other way around.
It's the other way around. Yeah, the holes are what you're going to find
When you factor in cost.
because it'll cancel out, right? If you factor and you can cancel it out, that'll produce a hole.
Yeah.
We can't factor an x minus 1 out of the top here to cancel out the bottom, so it's not going to give us a hole. It actually will give us a vertical asymptote at x equals 1. Okay?
Oh, so you're saying like if there was a hole there, then you wouldn't have vertical asymptote, right?
Yeah, if there was, say, an x minus 1 on the top here, where we could cancel it out,
We would just
then that would be a hole and there would be no vertical asymptotes.
Okay.
Okay? All right, now, let's talk about the horizontal asymptote.
None.
Why?
Because the degree is bigger on the top.
Yes, degree on the top is bigger, so this is the bottom. Okay? There are none. All right, so what we're actually looking here, this is what I was wanting to get at here. We're looking at a special case when there are no horizontal asymptotes. Okay? And that special case is going to be a case where we have what are called slant asymptotes. All right? Now this will only occur when we have all right, so we're looking at a special case here where the degree of the numerator is exactly 1 more than the degree of the denominator, okay? Now, if this were say, an x cubed on the top and an x on the bottom, we still would not have any horizontal asymptotes because it's bigger on top, but we also would not have any slant asymptotes because it's more than 1 degree higher. In this case, though, we have a degree of 2 on the top, a degree of 1 on the bottom, so we will have a slant asymptote. Now let me sketch one of these. This is not going to match our graph here, but I want you to see what this looks like before we actually sketch ours, okay? So let's say we have a vertical asymptote here. A slant asymptote is going to be something like this, okay? Here's our slant asymptote. All right? Now notice this will still divide our graph. It'll still divide our graph into 4 kind of regions here. All right? Just like the horizontal and vertical divided it kind of into quadrants, that were offset, but they were like quadrants. Here we have 4 parts to our coordinate plane, but they're kind of look like pieces of pizza or something, all right, on a badly cut pie. All right? Yes?
So, just like out of curiosity, the function on the test yesterday, where we crossed out like slant asymptotes, it did have a slant asymptote.
It actually did, yes.
Because like I graphed it on my calculator, and it looked
kind of goofy, huh? Yeah.
Like it didn't look like a normal.
Where did
And then I
you
put down a
get
horizontal asymptote.
vertical asymptote is -1?
This does not match the equation that we have over on the left. I'm just illustrating here, okay? If we have a vertical asymptote and a slant asymptote, then it's going to divide up our plane into 4 regions like you see here. And what's going to happen with the graph is you're still going to have that hyperbola look. But the hyperbola is going to look a little strange. Let me get back to a pen. Okay? It's going to approach the asymptote up here, and it might approach down here, and then you'll have the other half of it down here. Okay? Again, we're approaching the asymptotes here. The asymptotes just aren't perpendicular to each other. Okay? Or you might have, say, inside here, it might be a real skinny one, kind of going like this, where we're approaching the vertical asymptote, and then we're coming over here and we're approaching the slant asymptote. All right? So you have different possibilities for what this might look like. This is why we find the rest of these features, so we can then figure out what 2 parts it's going to be graphed in. Yeah, Kate?
So this can only happen when there's no horizontal asymptote, right?
Yes, that's correct.
Okay.
This will only happen if there's no horizontal asymptotes. Because it only happens when the degree in the numerator is bigger by exactly 1. Okay?
Yeah.
So if it's bigger on top, there are no horizontal asymptotes. Okay. All right, so let's get a couple of features here, and let's graph what we know so far. Our vertical asymptote is at x equals 1, so I'm going to graph that. Okay, there's our vertical asymptote. Our zeros, the zeros for this function. How are we going to figure out our zeros? Phoebe, how are we going to find our zeros?
Negative 3x squared plus 2 equal to 0.
Very good. Okay, in order for a fraction to equal 0, the numerator has to be 0, right? Okay, so we set that equal to 0. We get x squared equal to 2/3. So x is this plus or minus the square root of 2/3, right? Which is root 6 over 3 if you simplify that. Okay? Now, if you like, you can put those into your calculator. It's plus or minus root 6 over 3. That's less than 1. Okay, it's like 0.6 or something like that. But it's going to be here and here, you could say. Okay, so we put those on our graph. And one other point that's pretty easy to find is our y-intercept. Okay? Let's see, Chengo, how do we find a y-intercept?
X equal to.
Very good. Set x equal to 0. All right, and what do we get here if we set x equal to 0? Negative 2. That's right. Okay, so it's 2 over negative 1, so negative 2. So our y-intercept is this point, 0, negative 2. All right, so I'm going to put that on my graph right here. Now I have some points that'll help me. Once I get my slant asymptote, it'll help me to get this sketch going. All right, so here's the question. How do we get a slant asymptote? All right, let's look down here. The key to finding a slant asymptote is polynomial long division. Okay? This is one application of that polynomial long division. So you'll notice an asymptote has to be a line, right? So think about this. When I divide a quadratic, like I have here, negative 3x squared plus 2, by a linear equation, x minus 1, what am I going to end up with?
A linear equation.
A linear. What if I divided a cubic by a quadratic?
A linear.
I'd get a linear. That's why the degree has to be exactly 1 higher. If I had a cubic divided by a linear, I'd have a quadratic. That would not give me an asymptote. Okay? So, here's the cool thing about this long division. Notice here, we're doing the division, and we have the numerator on the top here. The numerator is the negative 3x squared plus 0x plus 2. We put that placeholder in there. We're dividing that by our denominator, x minus 1. Okay? Negative 3x squared divided by x is a negative 3x. We do the multiplication down here, and then we subtract. So it's minus a negative 3x squared minus 3x, and that's how we get this minus 3x, and then we bring down the plus 2. Okay? So now we do a negative 3x divided by x, and that's how we get this, negative 3 right here. Okay? And I actually could stop without even messing around with the rest of this. Because here's the thing, when we're talking about a slant asymptote, we really don't care what the remainder is. Notice here we got the linear part of this. All that's going to be left is the remainder. Okay? Now, it doesn't hurt to go ahead and find the remainder like they did right here. And we have a minus 1 as the remainder. But here's the thing. When you do this division, what you get here without the remainder is going to be what y equals for your slant asymptote. So it's going to be y equals negative 3x minus 3.
So you don't need to find the remainder.
No. You can just stop. Don't bother going on with the problem. Okay? Because you have what you need. Alright? So, now we can sketch. Here's negative 3. I have a slope of negative 3. Okay? Alright, so here is my slant asymptote. I made it nice and long here. Okay? So you can see here, you know, our slant asymptote is pretty vertical. I mean, it's not completely vertical, obviously, but It's pretty up and down, so we are going to either have a case where our graph looks like this, right? Or where it's going to be in here and it's going to be really skinny like this, okay? We have one of those two options, okay? But this is why we find these other points, okay? You'll notice here, these 3 points that we already know are in this segment of our graph right here. So I'm going to hit those 3 points. I'm going to come up and approach my vertical asymptote. I'm going to continue out here, and it's going to continue to get closer and closer to that slant asymptote. Okay? And then I can also, down here, I can sketch. This is going to approach these asymptotes here. Okay? And that's what that graph is going to look like. Does that make sense? Pretty much? Okay?
Can you leave that there for 1 sec?
Yeah. Alright. So this is how we would graph one. Doesn't have a horizontal asymptote, but it does have a slant asymptote. Okay? Kind of cool looking graphs.